Guys, so in this series we'll be talking about metric and topology at large. So it will be series and it will be broken down. So firstly we have to make some definitions to know what we're going to deal with in this course. All right, so we have two words here, metric and spaces. So when we're talking about space, I just want you to think about, when we're talking about empty space and there is a space, if you think of it that way. So we can say a space in mathematics is actually a set on which some mathematical structures such as notions, axioms, conditions, properties have been defined. So that shows this space is not empty, right? So that will be some definitions on the space. So we have vector space, we have linear space, and so on and so forth. So that is a space. Then a metric, which is very important here. So definitely we have to have a non-empty set. So that is the first thing. You have a non-empty set and set of real numbers. So we have set of real numbers. Those are the two things we need in defining a metric. Now a metric, you can say D, whatever you want to represent your metric with. A metric D on X is actually a real valued function so you can define it this way. You have the Cartesian product of your non-empty set mapped to the reals. Okay, so this is a real valued function such that it satisfies, that is your metric D satisfies the following axioms. Remember we define axioms on space. So now when D satisfies these axioms, then you can call D a metric. Okay, so for all x, y, z in X, so the first condition is called finite and non-negativity. So axiom 1 is 0 less or equal to dxy less or than infinity. That is the distance between 2 points y and x. The distance between point x and y is greater than 0 or equal to 0. We're going to talk about when it is equal to 0, right? But it can be equal to 0, right, when it is just 1 point, right? So that is when it is just 1 point, then the distance will be 0. The distance between x and x will definitely be 0 because it's just a point. So then this distance from x to y is actually finite. Finite means it is not going to infinity. Like if it is infinity, it goes forever. You don't know where it's going. But when we say finite, you know the beginning and you know the end. So that is what this axiom is saying, that it is finite and non-negative. That is, distance between this point and this point is actually positive. So that shows when we say non-negative is x, y greater or equal to 0. So it can be equal to 0, but it can never be negative. So now, we now say that it can only be 0, right, if and only if x equals y, which is what I said, right? So when we have a point, dxx, so here that shows x is equal to y here. So that is when we can have the distance between 2 points to be 0, when the 2 points is the same point, okay? So that is the second condition. So if you want to prove that D is actually a metric, you have to show this form. If and only if that shows two sides, you have to show when dxy is equal to 0, then x equals y. Then you show that when x equals y, dxy is actually equal to 0. So we'll do that in one of the series. Then the third condition is symmetry. So your distance from x to y is actually the distance from y to x. So that is what we call symmetry. Then the fourth condition is the triangle inequality, which says dxy is actually less or equal to dxz plus dzy. So the distance, right? The distance, this is x, this is y, and this is z. So we are moving from x to y. So we are saying when you want to move from x to y, is actually, when you move from x to y, is actually less, or it can be equal to when you move from x to z, then from z to y. So this distance is actually either equal, moving this way and this way, or it will be less than this way plus this way. So that is the triangle inequality. So when a metric D satisfies these four conditions, then you can call it a metric. Then the final definition will be a metric space. Because now we know a metric, we know a space. So the pair XD, where this is a non-empty set, and this is a metric, right? This metric is defined on this non-empty set. So this pair is called a metric space. So you know that this non-empty set, we have what? It is not empty. We've defined an axiom on this X. Remember, we say for every X, Y, Z in X. So it is not empty, and we define this metric, that is when it satisfies those conditions, then we call this a metric space. That is when this is actually a metric, then this pair will now be a metric space. So in the next video, we're going to check for examples of some metrics. So see you in the next video. Thank you.